Okay, good afternoon, everyone. Let's get started. So today we are going to talk about efficient GANs, videos, and point cloud understanding. We have talked a lot about general purpose application optimizations. So today we are going to talk about domain-specific application optimizations, focusing on GAN for image generation, video understanding, and point cloud. So why we choose these applications? On one hand, they are very computationally heavy, require a lot of compute. On the other hand, they have a lot of redundancy. For example, for GANs, it has 2D spatial redundancy. For videos, there's temporal redundancy. Between the frames, lots of frames are similar. So it's very wasteful to use 3D convolution to do that. And also for point cloud, there is also spatial sparsity. Not every point is actually occupied. So there's a lot of room for efficiency improvement. So this is the agenda for today. We will first introduce efficient GANs, including 3 techniques: GAN compression, how to compress GAN models, any cost GAN, how to apply this once-for-all technique to use a smaller GAN model for quick editing and prototyping, and finally using a larger one for finalization. And finally, the data efficiency. How do we use fewer number of images to train these GAN models? The differentiable augmentation for data efficient GAN training. Second chapter, we're going to talk about efficient video understanding, particularly the TSM, the temporal shift module. Finally, we are going to talk about efficient point cloud understanding, including point voxel, CNN, and also BB fusion. So let's start with the first part, efficient GANs. So GAN stands for Generative Adversarial Networks. It is a super popular technique for image generation. It consists of 2 parts. One is a generator, the other is a discriminator. So we train the generator so that the sample cannot be distinguished between the generated image versus the real image. To fool the discriminator that they are the same. And for the discriminator, the training purpose is to make sure it can distinguish between the real image versus the fake image. Okay, so therefore, there are 2 loss terms. To accelerate the inference, which should we improve the efficiency? Should we compress the generator or should we compress the discriminator? So at the generation time, only the generator will be used, right? The discriminator will not be used at the inference time. So the focus of compression will be the generator part. Okay, this is what we need to speed up. So this is a little bit of background of GANs. So this is learning to generate digits from MNIST, starting from random initialization, and finally we can generate those photorealistic images for handwritten digits. GAN has 2 categories. One is unconditional GAN, the other is conditional GAN. So for unconditional GAN, we use random noise. Feed the GAN model's generator with random noise to generate the output. Versus for conditional GAN, both the discriminator and also the generator are conditioned on provided labels, either a class label or the segmentation map or strokes. So this is the difference between condition versus unconditioned GAN. And this is a famous work, GAN from NVIDIA a couple of years ago for drawing. Can draw a stroke, and on the right-hand side, it can render an image. You can draw some mountains, and then it'll fill the mountains. And change the color to be grass and get a river out of it. So such kind of task prefers real-time processing, but GAN is pretty heavy. So this is another example of diffusion models for image editing. So here we added a dog. We're going to talk more about diffusion models in the next lecture. So although GAN is pretty powerful, such generative model is much more computationally expensive than these recognition models. Okay, for example, here we see the number of parameters, MobileNet, Resident 50. These are discriminative models, 4.2, 25 million parameters, but GAN is like 93 million parameters. versus the flops below 4 giga max versus 200 giga max. So it's pretty computationally expensive, which motivates us to compress these GAN models. And let's see how can we apply what we learned so far to GAN compression. So here we have a pretty large generator, and we want to compress it to be smaller by reducing the number of channels. Okay, so here we try to apply three losses. Okay, one is the reconstruction loss. For example, if we want to turn a horse into a zebra, we want to do pixel-wise, calculate the loss pixel-wise for each pixel to make sure it looks like a zebra. Okay, and also we have a distillation loss. Since the final reconstruction loss at the end is not enough, remember during distillation, we talk about we can also match the intermediate feature maps. Okay, so the feature map, the channel number is different. So we have to learn this one-by-one convolution, this projector, to project between a large resolution, a large number of channel versus a smaller number of channel. Okay, so that's the distillation loss in the middle. And finally, there's a conditional GAN loss, the original GAN loss. Okay. So finally, we put up together these three loss terms all together. And here we can use the once-for-all approach to train a super network, which is similar to what we did in lab 3 by changing the number of channels from small channel to large channel, randomly select the number of channels, and then fine-tune it to recover the accuracy. Okay. So finally, we can perform neural architecture research to select the number of channels that fit our latency requirement. So this is the result. This is the pixel-to-pixel models given the input strokes. These are the ground truth images. And this is the original model, pixel-to-pixel model, evaluating the truths. And this is the GAN compression, make it 11 times smaller. And it can match the quality is quite comparable with the baseline. On the right-hand side is horse to zebra. Input is a horse, the output is a zebra. And this is the GAN compression, compressed by 21 times. And the output still roughly the same, which is pretty cool. And here are some more examples, compressing GAN and given the segmentation input. And this is the ground truth. And this is the original GAN model. This is the reconstructed one. And this is a video demo showing the speed of horse to zebra before compression and after compression. So this is running on Jet7 Xavier GPU, mobile GPU, pretty small. Originally, it's very slow. It's running about 12 frames per second. And on the bottom, let's watch it again. On the bottom, now it can run 40 frames per second, much smoother, turning a horse into a zebra and running real time on a mobile GPU. Okay, so that's GAN compression. Now let's switch gear to talk about any-cause GAN for image editing. So the motivation is that GAN can be used for image editing, but the generation is pretty slow, making it difficult for us to run this image editing interactively on our laptops, on the tablets, etc. So the algorithm here is given an input image, we want to project it into a hidden space, into a latent space. Okay, and then we feed the point in the vector in the latent space as input to the generator, and then to generate the image. By tuning different knobs in the hidden space, in the latent space, we can control like smiling, hair, glasses, etc. Okay? So we can apply image editing by changing the latent space. However, this is pretty slow, which motivates us to find a way for very quick image editing. So how can we do that? The ray tracing example motivated us actually. So people can get very fast preview by reducing the number of sampled rays. For example, this is the 1,000 rays. This is 512, 128, 64. although the visual quality looks worse, but it's pretty quick, right? But here we want to make the compute less number of compute, but also make the quality hopefully as good as the full model. So can we do the same or even better for GANs? Actually, that make us motivated us to think about the Westphal network, right? So during editing, we can run a low-cost, smaller subnetwork. We have a super network, then we have a subnetwork. During editing, we can run a smaller subnetwork running at low cost, just as you did in Lab 3. For very quick preview. And after we are satisfied with our editing, we can run the full model. And the full model is slow, but with higher quality output. Okay, so this is the final finalized image. And hopefully, the finalized image versus the preview are very similar. They are consistent with each other. Okay, so that's our goal. And let's see how can we achieve that. So in order to specify, let's specify what dimensions do you want it to be the Westphal approach. Okay, so we want to change the resolution, support different resolution, and support different channel numbers. So the style GAN, so let's first see how resolution. How do we support different resolutions? During preview, probably uses lower resolution. During the finalization stage, let's use a higher resolution. Let's see how can we make it adaptable. The conventional work style GAN tool. So this is the generator from 32, 64, 128 to 56. Gradually increase the resolution and then feed the highest resolution to the discriminator to see if it is real or fake. MSG GAN feed all the resolutions from 32, 64, 128 to 56, feed every stage to the discriminator. Okay, that makes it more challenging because the discriminator has more information about the input. It has to be it has all the information across different resolutions, make it harder to pretend it to be a real image because for each resolution, it has to look like a real image rather than a generated image, not to fool the discriminator. So now we need to support different resolution. So it's even more challenging. We want to make sure for every stage that we generated 64, 128, or 256, all the resolutions, we can fool the discriminator, okay? Not only the highest resolution. So what should we do? And here we decide at training time, we randomly feed different resolution output to the discriminator. Okay, for example, here is a 256, now 64, 128, 256, 64, 128. We randomly sample different resolution to feed to the discriminator, such that when we are running at different resolution from 32, 64, all the way to 1K by 1K, our approach consistently have better FID, lower FID compared with a single resolution, like in this case, versus MSG GAN versus, which is all the resolution, and significantly reduce the FID at both low resolution and high resolution. Okay? So the sampling-based multi-resolution support, very similar to the discriminative model we built. However, this have an interesting phenomenon, right? So for style GAN, you see only at a high resolution it works, but when the resolution gets low, you can barely tell the image. But using our approach, it can smoothly transit between this is high resolution and this is low resolution, all the way to 32 by 32, okay? Versus it becomes completely noise. So this sampling approach is very helpful. Okay, so next, second goal, let's support different number of channels. Okay, we can run a full model with larger channel better quality, higher fidelity, versus we also want to support a smaller number of channels, make it faster, immediate inference, right? So here the approach is to sample adaptive channel numbers during training. Okay, sometimes 120 full channel, the number of yellow here indicates how much channel are we actually sampling. Okay, so here we are not only sampling different resolution, but also sample different number of channels as indicated in the yellow part. Okay, so we observed some inconsistency. For example, this is 100% of the channel. This is 50% of the channel. You see, actually, they don't look like each other. The lady previously has a pair of glasses. Now her glass is gone. Okay. How to solve this issue? We actually added this distillation loss to solve that issue. Okay, so make sure at a different stage we added this distillation loss so that the image at full channel versus half of the channel still look similar to each other. So we observed a second problem. When we are looking at FID for some of the subnetworks, for example, this is 20%, 25%. This is 25% for 128 resolution. This is for 256 resolution. If we're using the same discriminator for when it's at 256 channels, when the channel number is 25%, the FID suddenly spiked to 14. And the lower resolution, when the channel number is big, 50%, 75%, 100%, is also much higher than the vanilla model without this wide-fall approach, which is showing that using the same discriminator is not good. A single discriminator cannot provide effective feedback for different subgenerators. That makes sense if the generator is pretty weak, pretty slim, very few number of channels. The discriminator should also accommodate that. Using a single discriminator for big and small generator doesn't quite work well. So what should we do? We propose this generator conditioned discriminator. So the discriminator should be aware of the configuration of the generator. Okay, so here, this is the right-hand side is the discriminator, left-hand side is the generator. We collect the statistics, the architecture of the generator, like how many channels do we have, what is the resolution, and we feed it to an FC layer and use that to modulate the discriminator. We call it generator conditioned discriminator, such that the discriminator is aware of the size of the generator. And previously, the problem of same discriminator problem now can be solved, and even better than the vanilla approach. 7 reduced to 3. So the generator conditioned discriminator make it actually pretty helpful. So that's what's unique about this one small approach for GAN models. Since GAN model has two components, a generator and a discriminator, they have to be tightly coupled, make it a little bit difficult to optimize. And next lecture, we'll talk about a diffusion model, which has only one model to optimize. So finally, we can see some good results. So this is the forward consistency at different resolutions. So 124, 512, 128. And this is different channels, 100%, 75%, half, 25%. Okay, so they are very consistent and transit between different photos and different parts very smoothly. Which one has the lowest computation and can run fastest? So lowest resolution, right? The lowest resolution and fewest lowest number of channels. But still, it looks quite good compared with the full model. On the right-hand side, this is the lowest resolution and lowest number of channels compared with the full resolution, full channel. So we can also compare a different computation reduction. What does the quality look like? All these 4 images are generated by GAN, not real. We can reduce the MAC by up to 5 times. When the bar is shrinking, we can hardly tell the degradation of the quality of the image. 78%, 59, 39, 19%. Now we can apply it to photo editing. So this is a demo running on a laptop, a MacBook. Actually, that was a couple of years ago. I believe these days can run faster. Without any change, the original model is very slow, runs about 3 seconds, 3.24 seconds. So here we are making the man smile and also making him look younger by changing the sliding bar. Indeed, he looked younger and begin to smile. So here we can control different channels and different resolution. Now we can run it again. It's really fast. It's almost instant by shrinking the channel and shrinking the resolution. Now it's almost very interactive. So this is showing the latency. We can add some mustache, reduce the mustache. Finally, we click the finalize button to run the full model, which takes longer, takes 3 seconds. Now he looks much younger and look better. And try another image. Now we look older, change the hair color a little bit, make it gray hair. Make her look older is really associated with these eyeglasses. So we want to remove the eyeglass. So there's a sliding bar of eyeglass. We can push it to the left. And then the glasses are removed. Finally, we can click finalize to get a final high definition image. But this is open source. And it's rather deployable on a MacBook. So feel free to use this as part of your final project or discuss us if you have other ideas. All right, so let's talk about the third part. Having talked about the computation efficiency, now let's talk about data efficiency. So training GAN require a lot of data. It takes months or even years to collect a lot of data, especially label data. So annotation is pretty expensive too. Recently, there are some automated tools to automate the labeling process, but still collecting the data is pretty hard and suffer from copyright issue. There are some popular data set used for training these generative models. One of them is FFHQ, which contains 70,000 post-processed human faces. Another popular one is ImageNet, containing more than 1 million images of diverse categories. We tried training the GAN model with limited amount of training data. For example, using only 100 images to train the Obama face, but looks very poor. Or using 160 images to train the cat, it doesn't quite perform well. Or 300 images to train dogs doesn't work well. Okay, so although the original style GAN tool from NVIDIA works quite well, if we have a limited number of samples to feed it, the quality is very poor given limited amount of data. So this is the quantitative results, starting from 100% training data, lots of images, 20%, 10%. This is the FID. The FID keeps growing, showing the degradation of the quality given the less amount of training data. So the current techniques of GAN training lead to inferior results when the training data is very limited. And let's see why that happens. So this is the discriminators training accuracy versus the validation accuracy. With 100% training data, both of them, the training accuracy is pretty good. The validation accuracy is okay, But if we reduce the training data to only 20%, the training accuracy improved a lot. But the validation accuracy, not even the test, the validation accuracy dropped very significantly, showing that it's very hard to generalize. Not to mention if we go to like only 10% of training data, here the validation accuracy is even lower, okay? Very low validation accuracy, showing that the discriminator will overfit the small amount of training data, leading to worse generator performance because the discriminator is very poor. The generator cannot work well since they are tightly coupled. So that makes us naturally think about the data augmentation technique. If we have 10 images, then we can make one image becomes 6 images by rotating it, tinted with different color, by cropping it, etc. Okay. So traditionally, the data augmentation is a very effective technique to prevent overfitting. Then the question is, how do we augment GAN models? Okay, so one technique is to augment the reals only, the real images only. So there's a generator, there's a discriminator. We train the generator and the discriminator iteratively. Okay? Train them iteratively. And then one very popular technique is to apply these artifacts like color jittering, make it darker, make it brighter, apply color jittering, or apply some translation, like shift it to the top right corner, or apply some cutout, so cut a piece of image. If we augment the real images only, so the discriminator can take either the real image or the fake image. The fake image is generated. If we only augment the real image, what will happen? Actually, we find the generated image will suffer from the same artifact as we applied right here. For example, the generated image also look darker or brighter. The generated image also suffer from this translation. They also suffer from the cutout. The generated image have a big patch right here. That is because the discriminator sees the real image is already gone through this translation or color jittering, etc. So it believes the real image should also suffer from such transformation. Therefore, it encourages the generator to generate images like that. So this is not effective. Same artifact appear on the generated image. What if we apply a solution? Okay, natural solution is to apply this translation T not only on the real image, but also on the generated fake image. Okay, so therefore the discriminator believe the artifact doesn't have to come from the generator, but it can be clean and then later apply this translation. Okay, so we find it has very high accuracy on the TX, on the fake image, and the generated image after the translation, but it has very low accuracy on the GZ. Okay, so this is the GZ without the translation. Okay, so this accuracy is highly imbalanced. This unbalanced optimization makes training very hard, because when we are training the training generator, there is no transformation. When we are training the D, it has the generator. It has the translation. Okay? So what we need to do is actually apply the same transformation also during the training process of the generator. Make sure it is differentiable, so the loss can back propagate all the way to the generator when we are training the generator. Okay. So make sure both the fake image and the real image are applied the same transformation, and for the fake generated image, it can also back propagate to the generator. So the solution is to apply augmentation on both the real and the fake. This is the real, this is the fake. And for both the discriminator and also for both the discriminator and the generator. Okay. And immediately it solves the problem of the worst quality. Okay, so it no longer increases very quickly, but the FID stays pretty stable. It did increase a little bit because we have low data, but the FID becomes much more stable from 9 to 14 rather than from 11 to 36. And let's see, given this low short generation, if we apply differentiable augmentation, how does it look like? So this is the style GAN 2 baseline. This is style GAN 2 plus diff augment. So this is 100 images of Obama face. Now it becomes much better. This is 160 CAD, previously very bad. Now it's photorealistic. 300 dogs, much better. We can also interpolate across different images. So below images are all trained with only 100 images. For Obama face, cat, panda, different sceneries to interpolate between different seasons, between the night and daytime, works super well given only 100 images. All right, so let's take a short break before we jump into the next chapter about video understanding. Okay, welcome back. Let's switch gear to talk about video understanding. So video is the biggest big data. It's growing super fast, like 10 to the 5 hours of videos are uploaded to YouTube per day. It's probably outdated data. It's very essential for both the cloud and the edge applications. There's lots of applications related to video, for example, action, gesture recognition, scene understanding, video search for ads, and also for autonomous driving. The interesting new thing about video understanding compared with image is that we need to perform temporal modeling, right? Temporal modeling is very crucial. For example, given a single image, we cannot tell whether we are putting something from left to right or from right to left. Only if we watch the entire video sequence can we tell actually we are moving the tape from left to right rather than from right to left. Okay, so that's the interesting part about temporal modeling. There's also a lot of redundancy in temporal modeling. Okay, so like the background, the table stays exactly the same. The white paper stays there exactly the same. Only the foreground, which is the tape and the hand, changed its pixels. So we should exploit such redundancy for efficient video processing. So let's first visit 2D scenes for video understanding, and then 3D scenes, and then introduce the temporal shift module that give the 3D scenes performance, accuracy performance, but at a cost, computation cost at 2D scenes. So 2D scene based method. So in the history, a naive approach, actually very straightforward approach, is to sample frames and process with 2D scenes. And then we aggregate the scores for prediction, either using the average, the max pooling, or something. Okay. Another approach in the history is using this two-stream method. This is roughly published in 2014, about a decade ago. The first stream is the spatial stream for image. The second is the temporal stream, which is the optical flow. Okay, so optical flow is the vector indicating for each pixel where is it moving in the next frame. So extracting the optical flow is actually pretty computationally heavy. So it has two streams, one is spatial stream, one is temporal stream, and then fuse them together in the end. There's also an approach to combine the 2D scene plus late fusion, which is LSTM. to fuse the output from different CNNs. Frame 1, frame 2, frame 3, use the LSTM to fuse to do late fusion, and then give the final prediction, which is high jump. However, you can imagine such late fusion. What is the problem here? The low-level information is lost, right? Since the low-level information is extracted independently by different CNNs, only the high-level feature is extracted by the LSTM in this case. So let's summarize the pros and cons of 2D CNN-based method. Okay, so 2D CNN is very computationally efficient. We can also reuse 2D CNNs trained from image classification, image paths. But the bottleneck here is that algorithm the 2D CNNs cannot model the temporal information since each frame is processed independently. That's relatively low accuracy. And if you use optical flow itself, it's very slow to compute. And late fusion cannot model the low-level temporal relationships. So naturally, people think about using 3D CNNs for video understanding. So what is 3D CNN? The first work, very early work, again in 2014, a decade ago. This is the work called C3D. It involves not only the spatial dimension, but also the temporal dimensions. Okay? So this is a 2D convolution involved in the 2D space. And this is on multiple frames. We added L. Okay, so this is the 3D convolution, not only in the spatial dimension, but also in the temporal dimension. Okay, so can jointly model the spatial and temporal information by using 3D convolution to convolve over the videos. But you can imagine the 3D CNN, you added another dimension, it has more parameters. Right? It's pretty heavy. So can we inherit 2D CNN and make it become a 3D CNN? Okay, so actually, this paper called I3D can initialize 3D CNNs using 2D CNN weights. The weights are pre-trained by ImageNet on ImageNet. And how do we initialize a 3D CNN using 2D CNN? The technique is called inflation. Actually, the idea is to repeat the weight across the new dimension, repeat it multiple times to repeat the weights across the temporal dimension for initialization. The same weight repeated several times. For example, if you have a kernel size of 3 in the temporal dimension, you just repeat the original 2D CNN by 3 times to initialize that. And the 2D kernel now becomes a 3D kernel. So the pro and con here is that we can jointly model the spatial temporal information, which is a good thing. And can also model both the low level and middle level and also the high level information. But the con is that it has very high computation cost and also the storage cost, since we have to store a 3D, actually 4D tensor for the weights. And a lot more computation since we're adding one more dimension due to the actual dimension. So the natural question is, can we achieve 3D CNN's performance accuracy, but at 2D CNN's cost to get the best of both worlds? And actually that's temporal shift module, a new operation, which is neither 2D convolution nor 3D convolution, but shift. A very simple technique called shift. Let's see how that works. So this shift operation contains 0 flops, no computation, 0 parameter, no parameter, but it can very effectively perform temporal modeling. So let's see this step. Let's figure out the dimension first. So this is the temporal dimension. We have T1, T2, T3, T4 in 3 colors. And here is the channel dimension. Okay. So this is the original tensor without any shift. And here the depth is the H and W dimension. Here. So temporal shift, we can shift it both from the past to the future to the present, and also from present to the future. And so here, the first channel, the second channel gets shifted. Third channel, fourth channel, etc. didn't change. What happens here is that now T2 has certain channels, not only from T2, which is in this dark blue, but also channel from T1 in yellow, and from T3, which is green. So this T2 not only have T2's information, but also T1's information and T3's information. Therefore, it can combine the information by mingling across the channel. And you can do the one-to-one convolution across the channel to mingle the information from the past frame and also from the future frame. And how much percentage do we shift? That's a hyperparameter. You can imagine if you shift too little, you have too little information from the past and from the future. But if you shift too much, you have no information for the present, right? So that's a hyperparameter we should tune. So for offline video understanding, for example, you have 10,000 hours of video to process. This is a very good approach. Another scenario is that we need online video understanding, for example, for self-driving cars. In that case, we cannot shift from the future to the present since it's real time, right? So we can only shift from the past to the present. So here we are shifting from here T0 to T1, T1 to T2, T2 to T3, etc. Therefore, when we are doing a 2D convolution on each of them, on T1, for example, it has the information of both T1 and T0, okay? And so like here, it has information from T3 and also T2. The previous layer, T2 also has information from T1. So as a result, it has this diminishing weight all the way to the very first timestamp. So in this way, we use zero flops. Since the shift operation, you can just move the pointer without moving the data. And there is no parameter associated with the shift operation. Okay, so very effective technique to do temporal modeling in this way. And it can be inserted into off-the-shelf 2D CNNs. If you have a pre-trained 2D CNN, just off-the-shelf CNN to enable temporal modeling at a cost of 0 flops and 0 parameters. So let's see, how do we insert this temporal shift module into 2D CNNs? Start with the offline TSM models, for example, action recognition, fault detection, video recommendation, etc., where the frames are processed in a batch. So this is a video frame. This is different frames. They can be processed according to just the normal 2D convolution, and then you get different timestamps. Then you perform this shift operation so that at each timestamp, you also have the future frames information and the previous frames information. And you pass it to the next layer, and you have an identity layer to compensate for the information. The identity layer is actually quite crucial, because the first full channel in this case is lost. Current information is lost. That's compensated by this bypass layer. So that's offline, where you'll have access to both the future, the past time frame, and also the future time frame. This is online TSM module, like autonomous driving scenario. It's frame by frame processing in a streaming fashion from T+1 all the way to Fn. So what we do here is, after we compute part of the channels, we actually shift it out, cache in the memory. And for the next layer, we replace that channel with the previous time frames channel, okay, and shift out the current channel and feed it to the next timestamp. So as the timestamp goes on, this final layer has the information across all the layers, because at each layer you have its previous layers information. Okay, its previous layers information. So in the next timestamp, you have the previous layer and previous layers information. As a result, you can have access to the entire history of data. And the implementation is actually quite simple, can be done in just 5 lines of code. You can shift left, shift right, and some of them doesn't shift. Okay, so fold is a hyperparameter depending on how many divisions you want to have. Some of them you want to shift left, some of them shift right, and the remaining you don't shift. Very simple to implement. So let's see what is the performance of this temporal shift. This is the flops per video. Smaller the better. These are the TSM. This is the accuracy, pretty high accuracy compared with these baseline method and I3D method. Much smaller parameters as indicated by the size of this circle. It consumes 3x less computation than the ECO family and 6 times less computation than the non-local I3D family. So this is a demo for the something data set. Like here we are predicting on the bottom, hitting something with something. Now it's moving something away from something. It's real time. And covering something with something. It's rolling something on the surface. With something, putting something on the surface. Or hitting something with something. Okay. And this is comparing the latency about using 3D convolution on the top, about 164 milliseconds per video. But now it's much faster, about 17 milliseconds per video. About 9x speed up. At that time, we were still using P100. This is published in 2019. And this is about the throughput. The baseline method, about 6 videos per second. Now we can achieve 77 videos per second. And the accuracy is actually even better, 43 versus 41%. So this is for online video recognition. So process them frame by frame in a streaming manner. So this is across different data sets. This is the baseline. And this is the improved approach. The accuracy is improved a lot compared with baseline, double digits right here. And this is showing if we just observe rather than 100% of the video, and we watch only like 40% of the video, or only 10% of the video. So the top row is a TSM. Even if we are feeding it with like 10% of the video, the accuracy maintains much better compared with these baseline methods where the accuracy quickly drops. And this is a driving scenario for detection. So 100%, this is a car, but for the RFC method, which is detection frame by frame, it will misclassify it as a train, probably see in the headlight. This is quite dangerous for autonomous driving, since we want to make it stable. So frame by frame processing is a lot less robust compared with this temporal shift module, which has the history. It knows previously a car cannot suddenly become a train. For scaling down, temporal shift module is also having very low latency for low power deployment on just a Nano TX2 mobile phones, just a few watts, can run more than 20 frames per second on a CPU, and more than 70 frames per second on a mobile GPU, which is just a Nano. And scaling up, we also tried large-scale distributed training on the Summit supercomputer. This is the configuration. It has NVIDIA V100 GPUs at that time. So we are comparing several aspects. One is the throughput, one is hardware utilization, much better, 2x better than the baseline I3D method, since it has lower flops and better throughput. And here is showing the batch training time, compute time versus I/O time. So baseline method has a lot of I/O time, but TSM is purely dominated by compute time because TSM is very light in the I/O, decreasing the total batch time. And better scalability due to smaller model size, less weight to communicate for distributed training. Even with a large number of GPUs, the scalability is pretty high. So we are going to talk about distributed training technique starting from next week. How do we scale up the training utilizing multiple GPUs to speed up the training? So we can speed up training by 200 times using multiple GPUs from 2 days to only 14 minutes. So here is using one node. Here is using 256 nodes. One node is taking almost 2 days, 74.1% accuracy. And using 256 nodes, it takes only 14 minutes, just a cup of coffee. Coffee time, then you can train the model. Okay, get pretty much the same accuracy. So the theoretical speed up is 256 times, since we are increasing the node from one node to 256 nodes, and the actual speed up is 211x. So this is the accuracy versus the batch size. When we are increasing the batch size, this is the error. We can increase it all the way up to 12K batch size. So that's a perpetual issue. When increasing the batch size usually is associated with improved efficiency, but how to find the proper learning rate schedule to make sure a large batch size can still train well, that's a very interesting issue to explore. So this is showing the scalability as we are increasing the number of GPUs. What is the throughput? So TSM has the highest compared with different baseline methods like I3D methods. We can also dissect TSM to localize and understand what is happening. For example, channel 5 is understanding moving something away. So here we are highlighting the spatial and temporal pixels to understand why the model, TSM model, is thinking that we are moving something away. So these are the highlighted spatial and temporal information. There's a cup, now we move it away. There's something, now we move it away. There's a basket, and then we move it away. And channel 446 is understanding pushing something to the left. Here we have a cup, pushing to the left. It gets highlighted. Similarly here, we're pushing this box to the left. So we can also apply it to gesture recognition, since gesture recognition cannot be done in a single frame. Okay, so this is a Google Map navigation using gestures. You can use this approach, this gesture to switch between the street view versus the road view. And then you can enter the street view, you can zoom in, zoom out, etc. Go back to the map view. And this is done real time on a NVIDIA Jetson Nano. Okay, finally, let's talk about point cloud understanding, okay, from 2D to 3D vision. So there are a lot of 3D sensors widely used in our lives. Like the iPhone we have now have a LiDAR sensor. You can understand the distance, so you can use it as a measure the distance, measure the even 3D images, right? And also for self-driving cars, some of them has a LiDAR sensor on the top, drones. So what they collect is actually the 3D point cloud. So point cloud is a collection of points, X, Y, Z, together with the intensity as the with C dimensions as the intensity. Okay, so it's actually very sparse. If there is no object right here, there's actually no point. So in the 3D space, this is super sparse compared with images, 2D images, which has dense pixels. This has very sparse pixels, very sparse points. It has many applications, such as in autonomous driving. It can measure the distance and serve as another modality for the input. Also for augmented reality, this is the hallway at Stanford. Before the renovation, it was like when I was there, this was exactly the mapping. Now it's fully renovated. So for AR, VR applications. So the challenge is that point cloud is highly sparse and irregular. Okay, so like images is pretty dense. You have 1K by 1K image, so every pixel is occupied, very dense and regular. That can be processed by conventional convolution neural networks. But point cloud is extremely sparse. Okay, so sometimes it's more than like less than 0.1% density. Okay, the lower the density, the smaller the amount of pixels. And it's very irregularly stored in the memory, which GPU and parallel processing doesn't like, right? What we like is actually contiguous memory reference, regular memory access pattern, and large continuous memory footprint. But this is not the case. And we are suffered from the limited computation resource, right? For example, in AR, VR headsets, we don't want to have a whole backpack of computers, right? And a big battery we have to put in the pocket, and very heavy headsets. And also for self-driving cars, we don't want to have a trunk of workstations in the back. So these point cloud deep learning models must be deployed on resource-constrained edge devices. So we are going to introduce the PVCN, SPVCN technique to achieve higher efficiency for point cloud understanding. So let's first understand the bottlenecks for these point and voxel-based methods, which is two approach to deal with the point cloud. Okay. So for this is the resolution versus the distinguishable points versus the GPU memory, right? So as we are increasing the voxel resolution, as the resolution gets higher and higher, it's getting better for the distinguishable points. Okay? If the resolution is too low, we cannot distinguish the points because they are merged into the same voxel. Okay? If we want to achieve at least 60% of the points needs to be distinguishable, what is the memory requirement? And so when we are increasing the resolution, the memory is growing very fast. Actually, it's growing cubically with the resolution since it's 3D, right? So the memory grows cubically with the resolution. And here with only 8 gigabytes of GPU memory, more than 40% of the information is actually lost. On the right-hand side is showing the computational overheads. So this is showing the effective computation versus the dynamic kernel versus the irregular access for different point-based methods. So the baseline methods actually have a lot of overhead due to the irregular memory access and dynamic kernel computing. Well, our method, the PVCN, is actually spending most of the latency on the effective computation, not the overhead. So this is comparing the memory access, the bandwidth versus the energy, right? So this is multiply and add. This is SRAM read. This is DRAM read. So DRAM read, this is log scale. It's a lot higher energy compared with SRAM read and compute itself. So DRAM, off-chip DRAM access is much more expensive compared with arithmetic operation. Pretty low here and pretty high here. And the bandwidth is actually much lower compared with SRAM read. So we want to avoid the DRAM read. And random memory access is also quite inefficient due to the potential bank conflict. So what we like is actually a continuous address, like address 0, address 1, address 3, without any conflict. So what we are working on here is proposing an architecture called point voxel CNN. Okay? So we have 2 branches. One is the voxel branch, the other is the point branch. So for the voxel branch, we divide the 3D space into a grid of voxels. So here is a 2x2 grid. It's represented in 2D, but actually it's in 3D space. You can imagine as a 2x2x2 in the 3D space. And then we convolve it because it's very regular. So all these blue points, these three blue points will be associated with the same voxel. And this green point, these two green points will be associated with this green voxel. That's why we are saying the higher the resolution, the more distinguishable points. Otherwise, these three points are not distinguishable because they all fall into this blue voxel. Since now it become a very regular tensor, 2x2 tensor, we can do 3D convolution, and then finally we can devoxelize that. Okay? Assign the same feature for these three points. So that's basically modeling the neighborhood information, the adjacent info, the neighborhood information across adjacent voxels. And there's another branch which is focusing on point-wise operation, similar to the point net. We just transform the feature of individual points, okay, through this multi-layer perception, which is focusing on feature transformation rather than neighborhood modeling. So what is the advantage here? This voxel-based branch has much better regularity because it's a very dense tensor and there's no irregular access and dynamic kernel cost. It's very good for neighborhood and information aggregation. Well, this point-based branch can keep very high resolution since each individual point can be distinguished and can alleviate the information loss, which appeared here, like these all 3 points are fall into the same voxel and can no longer be distinguished. So that information can be alleviated by having this point branch to alleviate the information loss during the voxelization process. So let's see how does this two branch work well together. Actually, this voxel point branch is focusing on this large area like the tabletop, the chair, versus the point-based branch is focusing on those corners, like the legs, the corner of the chair, the legs, etc. Okay, very interestingly, small versus large, local versus global. So point voxel CNN is pretty fast and accurate. This is comparing the latency speed up more than like 7x speed up with the superior MLU, the accuracy, versus this is the GPU memory, much lower memory, but higher MLU. So pretty good memory and latency trade-off. So this is a demo for indoor 3D segmentation. So here is the point net, which is pretty slow, like 2 seconds. Now it's only 1 second. So what is the limitation for point voxel convolution? Actually, the voxelization phase in the PV-conv actually can introduce this information loss. So the voxelized scene, this is the input scene, this is a voxelized scene. So the person here and the person here becomes 4 dots and only 5 dots, okay? Because the voxelization is too coarse-grained. So what can we do to improve the resolution for this voxel branch without incurring too much high resolution? Actually, we can introduce this sparse point voxel convolution. Okay? So rather than using dense convolution, we can use sparse convolution on this branch on the top. So we first voxelize them and then run sparse convolution only on the voxels that is non-zero, and then we skip the computation on those 0 points. And that can have a better distinguishable points. So the point-based branch is actually focusing on those small objects and the person, the trunk, the side trunk, big trunk, etc. And then given the latency constraint, we can actually perform 3D neural architecture search to further improve the efficiency of point cloud understanding. So we're familiar with that already. We first train a super network by having fine-grained elastic channel number and also elastic depth number. This is changing the depth of different stage. And we have weight sharing between the input channel and output channel. Here we perform the evolutionary architecture search, very similar to what we did in lab 3. Given a super network, propose many candidate networks. If it fits the latency predictor, we keep the architecture, otherwise we sample again. Then we do mutation and crossover to search the best model. In this way, we can reduce the search cost by 17 times. And this is the reduce the GPU latency, reduce the max. All right, so we talk about both the camera and also the LiDAR, the image, and also the point cloud. Now let's fuse them together. So this is a common scenario for autonomous driving cars. It has multiple multi-view cameras. This is actually in the Seaport area in Boston. So it has a front camera, front right, front left, back camera, back left, and back right. It also has a LiDAR in the 3D view. So how do we fuse multiple sensors information together in the same space and perform perception in that shared space? So what is that shared space? It needs to be easily converted for multiple modalities without much loss of information. Okay, and it also should be suitable for different 3D perception tasks like object detection and also map segmentation. Our solution is using the bird eye view, to fuse them. Okay, so the LiDAR feature exists, we can project it in the bird eye view. And also for the camera feature, we can also project it in the bird eye view. So bird eye view basically look at the world from the top, right? From the top, so that we can mash them together, fuse them together. Just like we give an example here, this is in the Vassar Street, in the CCL building. This is the camera view, perspective camera view. And this is the bird eye view, okay? From the top down, this is the CCL building. Okay? So we want to do this view transformation to transform from this camera view to this bird eye view. And for all the sensors to fuse their information in this shared space. So here is a popular configuration for self-driving car, multiple cameras, multiple LiDARs, several radars, okay? We can fuse the information across multiple sensors that consist of dense images and also the sparse point cloud. And there will be two branches of data flow. One is the dense branch for the camera. The bottom is the sparse branch for the LiDAR. And we merge the information in the bird eye view space, in the BEV space, which need to convert. We first pass it through a camera encoder to get the camera features. And we perform this camera to BEV, this view transformation, which is actually we accelerated a lot for this critical operator to cast it into the BEV space. For the LiDAR sensor, we pass it through a LiDAR encoder to get the LiDAR feature, and then we flatten that in the Z space, assuming that no car will be laid on top of another car. So we can flatten that in the Z space, Z axis, and get the LiDAR feature in the BEV space. Then we can concatenate the information together, pass it through the BEV encoder to get the fuse the BEV features. And we can use multiple heads to decode that. One head for the map segmentation to get the road, and the other for the 3D detection to get the bounding box for the cars. It can, so this is the demo of BEV fusion using multiple sensors as the input to do joint 3D object segmentation for the cars, and also the BEV map segmentation on the right. When it was released, it's actually running the top on the Waymo leaderboard. Okay, so that's all for today's lecture. We'll talk about domain-specific acceleration techniques, including GANs for image generation, GAN compression, any-cause GAN, and also differentiable augmentation for data-efficient GANs, followed by the video understanding using temporal shift module using the shift operation, very cheap for temporal modeling. Finally, point cloud recognition, which is using PVCN, SPVCN to accelerate the point cloud recognition. In the next lecture, we'll introduce diffusion models